This is the introductory video of the series on science and nature. It covers some of the most notable events in the history of the universe based on current scientific knowledge and evidence. Let's begin with the question of when did the universe start? Scientific evidence collected in the last 100 years shows that the universe is expanding. Albert Einstein's general relativity equations describe how matter, energy, space, and time interact with each other on very large scales. It is the best scientific tool to explain, model, and predict the current expansion. It can also be used to simulate how the universe has evolved in time. This exercise shows that in a very distant past our universe was very small, very hot, and very dense. Progressing with the equations further back reduces the universe to a single point with infinite density and temperature. This is known as gravitational singularity. General relativity equations describe how matter and energy distort space and time. This distortion then dictates how matter and energy behave and flow in the universe. Gravity in general relativity is not a force but a perception of the deformation of space and time by the matter and energy. No other interaction between matter, energy, space, and time are included in general relativity equations besides the ones perceived as gravity. On the small scale of the small, hot, and dense universe, gravity is overcome by the effects of the remaining fundamental forces of nature, namely the electromagnetic, weak, and strong nuclear forces. Therefore, general relativity equations alone are not capable of describing the physics of this infant universe. Another model is needed for this early stage. The Standard Model of Particle Physics is a scientific model that incorporates the electromagnetic force, the weak nuclear force, and the strong nuclear force. The model also explains how those forces interact with the elementary particles that carry mass and forces. This is the tool used to explain the initial stages of this hot and dense universe. Combined, Einstein general relativity equations and the Standard Model of Particle Physics are the basis for what is called the Big Bang model. The Big Bang model does not describe how mass, energy, time, and space were caused or created, but rather it describes the emergence and expansion of the present universe from an ultra-dense and high-temperature initial state. Experiments have confirmed that at higher energy levels, the electromagnetic and weak nuclear forces unify into a single combined electro-weak force. This led to the speculation that as we regress further in time, at even smaller scales, all those three fundamental forces of nature were unified into a single force, in what is known as the electronuclear force. In the Grand Unified Theory, the electronuclear force is used to explain the extremely brief and early phase of the universe, known as the unification epoch. Unifying gravity with this electronuclear force will provide a more comprehensive theory known as the theory of everything, but this has not been achieved yet. In later videos we will go over details of the Big Bang model, but for now it is sufficient to know that the model predicts that the universe started to expand from a very hot and dense state about 13.8 billion years ago. This expansion was not uniform. Tiny fluctuations of energy and matter concentrations led later to the formation of a heterogeneous structure with several astronomical objects such as gas clouds, galaxies, and stars. Galaxies begin as gas clouds swirling through space. As other clouds get closer, gravity sends these objects colliding into one another and knits them into larger spinning packs. Subsequent collisions can sling material toward a galaxy's outskirts, creating extensive spiral arms leading to the formation of the first galaxies. The best scientific estimate is that our own galaxy, the Milky Way, is 13.6 billion years old and was formed like many other galaxies, within the first few million years after the Big Bang. Within a galaxy, gravity continues pulling together clumps of matter across it. Eventually this leads to the formation of local disks, with the center filled with hydrogen gas forming what is known as a protostar. As the temperature inside this protostar increases, nuclear fusion begins transforming hydrogen into helium, releasing largest amount of energy in the process. While the star is being formed, gravity continues lumping small clumps of matter into larger ones within the surrounding disk. Eventually, this process thins out the gas and debris around the star, collecting them into the several larger objects, known as planets and asteroids. A few 100 million years later a new solar system is formed. Stars and planets were created together in billions of sites across the Milky Way, and other galaxies by this process. Science estimates that our own solar system is 4.57 billion years old. Earth is estimated to have formed into a distinct object with a crust, mantle, and core about 4.55 billion years ago. Our solar system lies next to a partial arm of the Milky Way called Orion Spur, located between the Sagittarius and Perseus arms. The distance between astronomical objects is exceptionally large. Scientists use the fact that the speed of light is constant in vacuum to measure those large astronomical distances, by comparing it to the time that light takes to cover the same distance. The speed of light in vacuum is approximately equal to 300,000 kilometers per second. So, 1 light second corresponds to 300,000 kilometers. The average distance between the Earth and the Sun is 150 million kilometers, or around 8.3 light minutes. The closest star to the solar system is Proxima Centauri, which is roughly 4 light-years away from our solar system. The Milky Way galaxy's diameter is around 100,000 light-years. The closest independent galaxy to the Milky Way is Andromeda and is located 2.5 million light-years from us. The Andromeda and the Milky Way are in a collision course, expected to occur 5 billion years in the future. If you are interested in learning more about cosmology, visit some of the many cosmology and astronomy observatories and research centers. Even a trip to your local planetarium or science museum will add interesting information about the universe. Armed with a smartphone Sky Map app, you can explore the universe in Dark Skies Preserve. Dark Skies Preserves are areas where light pollution is kept to a minimum. They are usually located around parks and observatories or just remote locations far away from large population centers.